Module 2 of our course is all about the Rankine's active and passive pressure. So we have here a graphical representation to illustrate the Rankine's active pressure. We have here your wall AB, say a retaining wall, and then we have here your soil. So we have here your soil sample wherein a vertical stress is acting on it, at the same time a horizontal is acting on it. And then if a wall tends to move away from the soil, a distance of delta x, the soil pressure on the wall at any depth will increase. So if we have a displacement denoted as delta x, this is where the moves or the wall moves towards the left. Wall movement is towards the left, or it is moving away from the soil. So this is active pressure, Rankine's active pressure. So if the delta x is equal to 0, effective stress, effective horizontal stress is equal to the coefficient at rest multiplied by the vertical stress. So if the wall is not moving, it is static, delta x is equal to 0. So let us now go to another working equation for Rankine's active earth pressure, and that is sigma prime A, and that is given by sigma prime A, or the Rankine's active earth pressure, is equal to the unit weight of the soil multiplied by the depth multiplied by tangent squared 45 minus phi divided by 2 minus 2c. C prime here is the cohesion multiplied by tangent 45 minus phi prime divided by 2. So from our previous coefficient, we have said that coefficient of active pressure is tangent squared multiplied by 45 minus phi prime divided by 2. So observe that this quantity is the same as this term as well. So if we want to simplify, or simplifying this Rankine's active earth pressure by substituting this term, we come up with Rankine's active earth pressure is equal to the unit weight of the soil multiplied by the distance multiplied by Ka, which is this one, and then minus 2c, the square root of case of A, or coefficient of active pressure. So we have here the pressure diagram for the Rankine's active pressure, and note that this is the same equation. This is also a graphical presentation of the equation. So that becomes the unit weight, the vertical stress, multiplied by the coefficient, minus 2c prime, the square root of case of A, is equal to the Rankine's active earth pressure. And from the diagram, we have here the diagram for Rankine's earth pressure. And notice that at z is equal to 0, when z is equal to 0, we have a value for Rankine's active earth pressure that is given by 2c prime multiplied by coefficient of active pressure, or this quantity, or this value on this part. So this indicates a tensile stress that decreases with depth and becomes 0 at a depth of zc. So notice that as the tensile stress decreases, there will come a time that it becomes 0, and that distance is denoted as z of c. The depth z of c is the depth of tensile crack. It is called the depth of tensile crack because the tensile stress in the soil will eventually cause a crack along the soil wall interface. So z of c can be solved with the following equation, that is 2c prime divided by the unit weight of the soil multiplied by the square root of the coefficient of active earth pressure. So the total Rankine active force per unit length of the wall before the tensile crack occurs is, so before the tensile crack occurs, meaning to say before the tensile crack reaches this point, the 0. So the Rankine active force is given to be 1/2 multiplied by the unit weight multiplied by h squared multiplied by the coefficient of active earth pressure minus 2c prime multiplied by the h or the height multiplied by the square root of case of A. So in short, this is actually the area of this pressure diagram. So if we are to project this part, we can form a big triangle. But notice that instead that we add the distances, since this is going towards the negative side, this becomes negative. Kaya minus itong part na to. And then, the total Rankine active force per unit length of the wall after the tensile crack occurs is the hatched area. So, after the tensile crack occurs, this is at this point, towards this point. So, what we will be considering is just the area of this triangle or the hatched area, just this part. So, what is this area? That is simply the area of a triangle, and we need this distance. But we can solve this distance. This is h. H is the total distance less z of c. So, putting that into an equation, that becomes 1/2 multiplied by the height, which is h minus z of c, multiplied by the base. So, the base is the vertical stress. And if you are to expound that, that is simply the unit weight multiplied by the height, multiplied by the coefficient of active earth pressure minus 2c prime, multiplied by the square root of case of A. So to further understand the concept of the Rankine's active earth pressure, let us try to consider a problem. A 6-meter high retaining wall is to support a soil with unit weight 17.4 kilonewton per cubic meter with a soil friction angle of 26 degrees and cohesion is equal to 14.36 kilonewton meter squared. Letter A, determine the Rankine's active force per unit length and the line of the action of the resultant of the wall before the tensile crack occurs. Letter B, determine the Rankine's active force per unit length and the line of action of the resultant of the wall after the tensile crack occurs. So first things first, we have to identify the given so that it will aid us in solving the problem. Unit weight of soil is given to be 17.4 kilonewton per cubic meter. Soil friction angle or simply angle of friction is 26 degrees. Cohesion is given to be 14.36 kilonewton per meter squared. So next is letter A and letter B. So if you're going to put this into symbols so that you will not be reading it in a statement, required is, and also by the way, each height of the wall is also given to be 6 meters. And then required is simply the active force per unit length and the line of the action of the resultant. So the line of action of the resultant is simply the z bars of z, which means that where is this force acting on the height of the wall. So saan siya nag-act? So that is bars of z. So case 1, before the tensile crack occurs. Then letter B is after the tensile crack occurs. So first things first, we have to determine the value of the coefficient of Rankine's active earth pressure. So that is case of A is equal to tangent squared multiplied by 45 minus the angle of friction divided by 2. So since given ang angle of friction, we substitute the 26, the given, and we come up with a value, case of A is equal to 0.39. So since this is a coefficient, it is a unitless value. And then next is we determine the value of the Rankine's active earth pressure. So do not be confused. This one, Rankine's active earth pressure. This one, coefficient of Rankine's active earth pressure. So this one is coefficient. This one is not a coefficient. So this one has already a unit. So before we continue to solve the problem, if the soil is given to be cohesionless, so if C prime is equal to 0, the Rankine's active earth pressure is simply case of A multiplied by the vertical stress. Or if we are to expound this simply becomes case of A, and then vertical effective stress, that is simply the unit weight of the soil multiplied by the distance. So if we are to take a look at the diagram, so kapag cohesionless siya, sabi natin C is equal to 0. So if it substitute 0 in this value of C prime, eventually all this term becomes 0. So we are left with this equation, which is the same as this one. Okay, so same here. If we substitute 0 on C prime, eventually this will become 0. So again, kapag cohesionless yung soil, kapag C is equal to 0, the Rankine's active earth pressure is simply a case of A multiplied by the unit weight multiplied by the distance. Okay, but since in this particular problem, the soil is cohesive, we have a value of cohesion, then we will be completing the equations to be used. So kapag ganun, let me just erase this part. Alright, so again, since we have a value of C, hindi siya cohesionless, but it is cohesive, let us now determine the Rankine's active earth pressure. So at Z is equal to 0, we already have a value. So active earth pressure is equal to negative 2C prime multiplied by the square root of Ka. So we simply substitute the values since cohesion is given and the value of the coefficient is we were able to solve. That becomes negative 2 times 14.36 multiplied by the square root of 0.39. So at Z is equal to 0, the Rankine's active earth pressure is negative 17.936 kilonewton meter squared. So it is consistent with the sign and the diagram is consistent. Next, at Z is equal to 6 meters. At Z is equal to 6 meters, so Rankine's active earth pressure is equal to, we just substitute this equation. So 17.4, the unit weight of the soil is given. The depth that we are considering is 6 meters because at Z is equal to 6 meters. And then the coefficient, which is 0.39, minus 2C prime, the square root of Ka, or notice that this one is this value. So that simply becomes 17.936. So simplifying, at Z is equal to 6 meters, Rankine's active earth pressure is equal to positive 22.78 kilonewton meter squared. So since we were able to solve for the value of the coefficient of Rankine's active earth pressure and the Rankine's active earth pressure, we can now determine the value of the force per unit length before the tensile crack appeared. So in our previous discussion, we have said that the force per unit length is simply the area of the pressure diagram. So we have here the pressure diagram for Rankine's earth pressure. So you choose either you use this one on the left side or the total already, whichever is more simple to manipulate. Anyway, both are equal. So for this particular problem, let us use the triangle and the rectangle because it is more simple. So force per unit length is equal to area of the triangle 1/2 times the unit weight multiplied by h squared multiplied by case of A minus area of rectangle, that simply becomes 2C prime multiplied by the square root of Ka multiplied by the height. So substituting, since all the parameters are known, that becomes 1/2 times the unit weight of the soil times the height, which is 6 meters squared, and then multiplied by the coefficient, the one we were able to solve, 0.39, minus 2 times the value of cohesion, this is given, 14.36, times the distance, 6 meters, times the square root of the coefficient of Rankine's active earth pressure. So PA now, or the force per unit length now, is 14.534 kilonewton per meter. Next, we are to determine the where the resultant determine where the resultant is acting. So where is the piece of A acting from the wall? So the line of action of the resultant can be determined by taking the moment of the area of the pressure diagrams about the bottom of the wall. So since we already determined the area of these two, then we take summation of moment of the area towards the bottom of the wall. So that simply becomes bars of Z is equal to the summation of the moment of area divided by the force per unit length. So that becomes the area of the triangle, 22.148 kilonewton per meter squared, multiplied by the lever arm. So if you take summation of moment at this point, lever arm for triangle is 1/3. So if this is 6, this becomes 6 all over 3. Minus the area of the rectangle is 107.6138. Lever arm for rectangle is half. So that becomes 6 divided by 2 divided by the force per unit length. So bars of Z is equal to negative 5.432 meters. So the negative sign indicates that the pressure is acting on the tensile part. So negative 5.432 meters from the bottom of the wall. So it's somewhere here. Next, we determine the value of the force per unit length after the tensile crack appeared. So after the tensile crack appeared, this is already this part. So before, lahat kino-consider natin. After, if this is the 0, and this is where the tensile crack appeared, then this is only the area that we are to consider. So first, sabi natin, piece of A, force per unit length, is the area of the pressure diagram. So this time, gamitin natin itong itong total pressure diagram. Yung kanina, ginamit natin yung nandito sa left side. Yung ngayon, gamitin natin ito. So, since this is the area that we are to consider, we would be needing this height, this distance, and that is simply the total, which is h minus z of c. So we have to determine the values of z of c, and then we subtract it from the total height for us to be able to get this height. So to determine z of c, that becomes 2 times the cohesion, 14.36, divided by 17.4 kilonewton per cubic meter, multiplied by the square root of a case of A. So cubic meter and meter squared will cancel out. We are left with meter. So 2.643 meter. So let us now get the area of this triangle, which will serve as our piece of A. That becomes 1/2 times this distance, that is h minus z of c, multiplied by the base. So this is the base, unit weight multiplied by the height, multiplied by the coefficient minus 2c prime, multiplied by the square root of the coefficient. So substituting the value, since all parameters are known, we simply direct substitute it, and we come up with the force per unit length is 38.237 kilonewton per meter. Uh, just like in the active earth pressure, the slip lines or the failure planes in the soil mass will then make an angle of 45 minus angle of friction divided by 2 with the horizontal. So the coefficient of Rankine's passive earth pressure is given by case of P. P stands for the passive is equal to tangent squared multiplied by 45 plus angle of V divided by 2. So what has been changed? In the active, this is minus sign or negative sign. In the passive, this is plus sign. So this is an example of the Rankine's passive earth pressure diagram. So Rankine's passive earth pressure is given by unit weight multiplied by z tangent squared multiplied by the quantity 45 plus angle of friction divided by 2 plus 2c prime multiplied by tangent 45 plus angle of phi divided by 2. So from the coefficient, we have said that the coefficient is equal to tangent squared multiplied by 45 plus the angle of phi divided by 2. Again, we substitute this value to this value to simplify our equation. So Rankine's passive earth pressure is equal now to the unit weight of the soil multiplied by Z multiplied by the case of P, which is the coefficient, plus 2C prime, the square root of case Kp. So the passive force per unit of the wall can be determined from the area of the pressure diagram. Okay, so let us consider a sample problem. A 3-meter high wall is shown. So this is a wall, retaining wall, 3 meters in height, and determine the Rankine passive force per unit length of the wall. So notice that we have 2 layers of wall. We said it's 2 layers because first and foremost, the first layer is dry, we assume, because we have here the presence of groundwater table. So on this part, it's saturated. On this part, it is not saturated. Other than that, if we are to check the parameters, both soil have different unit weight, has a different also angle of friction, and have a different value of cohesion. So we have here the layer 1 and we have here the layer 2. Thus, we have 2 values for the coefficient. So first, we have to solve for the value of coefficient of passive earth pressure using this equation. Kp is equal to tangent squared multiplied by 45 plus the angle of friction divided by 2. So first, let us determine the coefficient on the first layer. That is designated as 1. So that becomes tangent squared multiplied by 45 plus the angle of friction is 30 degrees. So 30 divided by 2, this is 3. And then next, considering the second layer, case of P is equal to tangent squared multiplied by 45 plus the angle of friction is 26 divided by 2. This is now 2.561. We will be using a tabulation for the presentation of our solution for this problem. So first, let's just put here the value that we solve for the coefficient of pressure for the first layer of soil, that is 3. And then for the second layer of soil, that is 2.561. Alright, so our goal is to solve for the passive earth pressure given by this equation. And notice that this unit weight multiplied by Z is actually your vertical stress. This one. Okay, so let's start. First is at Z is equal to 0. At Z is equal to 0, so obviously there is no load. So our vertical stress is 0. But if there is a surcharge load dito sa taas, then you consider the surcharge load sa pag-solve ng vertical stress. But since wala namang surcharge load on this particular example, vertical stress at Z is equal to 0 is simply 0. And then for the pore water pressure, by the way, I've placed here a column for the pore water pressure. So kahit na wala naman talaga siya sa equation ng passive earth pressure, naglagay pa rin tayo ng column for water earth pressure for the purpose of the plotting of the pressure diagram later on. Okay, so pore water pressure at z is equal to 0 is 0, and then of course that simply becomes 0 times 3, that is 0. Next, at a depth of 2 meters just above, and we have another 2 meters just below. So since this is the boundary, we will be considering different the two parameters for the first layer and the second layer. So for now, let us consider 2 meters just above. So vertical stress at that point, that is simply unit weight times the distance, that is 15.72 times 2. So 15.72 times 2 is equal to 31.44. And then again, still, the pore water pressure is 0. And then solving for the passive earth pressure, this now becomes, notice that the first layer is cohesionless because C1 is equal to 0. So this term of the equation will be eliminated because eventually kapag sinubstitute natin yung 0 sa C prime, mag-cancel out lang din ito dahil mag-0 siya. So we are left with this equation. So again, itong unit weight multiplied by z, this is also your vertical stress, which is 31.44. So this becomes 31.44 times the coefficient, which is 3. This is 94.32. Next, at 2 meters just below, so still vertical stress is still the unit weight multiplied by 2. So same pa rin yung vertical stress natin at 2 meters. And then of course, no water. And then since we're already considering just below, we will be using the parameters of the soil below. So this time, meron ng value yung cohesion natin. This is already a cohesive soil. So we will be considering this term. So substituting, that becomes now 31.44, this value, multiplied by case of P, which is 2.561, plus 2 multiplied by the cohesion, it's given to be 10, multiplied by the square root of Kp, 2.561. So this is 112.524. Next, at a depth of 3 meters, so that is 2 plus 1, at a depth of 3 meters, the vertical stress at this point is simply all the stresses or the weight of the soil that it carries. So lahat ng mga weight of the soil sa above niya ay i-consider natin. So that becomes, first is, at this point, yung stress or yung weight ng soil at this point na nakuha na natin. So that is 31.44. So we simply put it here, 31.44 plus, considering naman itong second layer. So that becomes unit weight saturated, 18.86. Since this is a unit weight saturated, minus 9.81, the unit weight of water, times the distance, which is 1 meter. So shortcut lang ito, parehas lang din. So if we are to consider the equation for the vertical stress, that is simply total stress minus pore water pressure. So that becomes 18.86, yung unit weight ng soil, 18.86 times 1 minus yung pore water pressure, 9.81 times 1. So this is just a simplified way of writing it. Okay? And that is 40.49. And then the pore water pressure, 9.81 times 1 is simply 9.81. And then we have here passive earth pressure. So that becomes now 40.49 times the value for the coefficient, 2.561, plus 2 times the cohesion. So the cohesion is given to be 10 multiplied by 2.561. That becomes now 135.701. Okay, so these values of the passive earth pressure, we will be using this to plot the pressure diagram, and from there, solve for our force per unit length. Okay, so let's plot first. Ang ipa-plot natin ay itong earth pressure and yung pore water pressure. Passive earth pressure and pore water pressure. So the first diagram you see here is a plot of passive earth pressure, and then the second one is the plot of pore water pressure. Okay, so at z is equal to 0, at a depth of z is equal to 0, the earth pressure, passive earth pressure, is equal to 0 also. And then at 2 meters just above, that is 94.32. So from 0, we go to 94.32. And then next at 2 meters, still at 2 meters, we have a value of 112.254. So we are still at 2 meters, and then we move to the increasing part. This is 112 point. Please disregard the decimals, no? So in the actual computation, I used 3 decimals, so there is short discrepancies. Alright, so going back, that is 112.49. And then at a depth of 3 meters, that becomes now 135.701. So from 112, this now becomes 135.65. And then we have here the pore water pressure. So at z is equal to 0, so no value for the pore water pressure. At 2 meters, this is our 2 meters, still we don't have a value for the pore water pressure, so 0 pa rin siya. And then at z is equal to 3 meters, we now have a value of 9.81. So in our diagram, at z is equal to 3 meters, that is 9.81. Then, sabi natin, the passive force per unit of the wall can be determined from the area of the pressure diagram. So, the force per unit length is simply the area 1 plus the area 2 plus the area 3 plus the area 4. So, substituting area 1 is just the area of triangle. That is 1/2 times the base is 94. Just this part, 94. And then the height is 2 meters, right? So the first layer is 2 meters, the second is 1 meter. So 1/2 times 94.32 times 2 plus area 2, the area of rectangle. That is simply, the area of rectangle is this value is 112. So 112.49 times the height, which is 1 meter, plus this triangle, area 3. So the base of this triangle, we can solve that by 135.65 minus 112.49 times the height, which is 1 meter. And then finally, the area, area 4, that is 1/2 times 9.81 times the height is 1 meter. So simplifying, the force per unit length, passive force per unit length is 122.385 kilonewton per meter. All right, so we will be considering other examples in the next video presentation.